To go on lecture 10? So let me say what lecture 10 is about. It's going to bring back, it won't be entirely about what we did before, but it's going to bring back these matrices. You remember this was K4 from the first lecture with 2's all the way along the diagonal. And then T4, the one with a change at the top, change that 2 to a 1. And then I don't know if I gave this one a name. This is the one where the change is down at the bottom. And so it's really just, it's very, very closely related to this guy. Just the changes, H maybe is for hanging, because this was the change came at the bottom when we had those springs and masses hanging in a line, where the change came at the top if the top boundary was free. So this is fixed at both ends. And this one is free at the top and fixed at the bottom. And this one corresponds to fixed at the top and free at the bottom. Okay. So, one thing to do, which we posed as an exercise or a problem, was to figure out what was going on with the inverses. And these inverses are very pleasant. And we can capture those very quickly. And by the way, everything I say about H is going to come very immediately from everything we say about T. So those two are really the same job. But K provided a not so obvious question. And I opened on the web page the question of finding formula for the inverse matrix, and suggested to take the 3x3 or the 4x4 case as examples. And here, let me see what the inverse is. Ooh, I've got it written down. I remember the 1/5, and so what does the 5 represent there? In an inverse, you're always dividing by the determinant, and the determinant of the 4x4 matrix is 5. And in general, the determinant of the n by n matrix is n plus 1. So that part of the pattern we could spot, but this was maybe not, well, this looks pretty clear along the top row and the column and the row. Of course, turning it upside down isn't changing anything here, where turning this one upside down converts to that one. And turning that one upside down should convert to this one. But now the numbers that came in here were not so... The pattern there was to be discovered. Or guessed. So one approach is guess and verify. And several people did that quite successfully. Made a good guess there. Or they may have reached their formula by some systematic. I shouldn't say they guessed, because they may not have. They may have done it differently. But I couldn't see what was the best way. So the question is how to find these inverses. And I kind of puzzled about that for quite a while. And then as I caught on to how to do it, I saw more of the pattern. And I saw the connection between these equations with matrices K or T and these equations with these differential equations that we looked at in a later lecture. So the differential equation that we looked at was, remember, what's the connection of minus, what's the connection between that differential equation, the left side, and these matrices? Let's see, these matrices, in words, what kind of matrices are we seeing? We're seeing in a typical row of these matrices, minus 1, 2, and minus 1. Yeah, and what do those three numbers, what jumps to mind when I see those three numbers? It's a second difference, where here we have a second derivative, and we have a minus sign, and actually, we've got a minus sign here too. The true second difference would be 1 minus 2, 1, and we've switched those signs. Okay. Now, all right. Where should we start? I had several ways to approach the inverse, the question of the inverse. So let me take this easier one first. To say, how did we get to the inverse of that? And the way, a good way to get to the inverse of that is starting with t, of course, and we've got to get there. Of course, we could check it that it works, but that doesn't seem quite fair anymore. So let me take that matrix and factor it. You remember how it factored? So I'm going to concentrate on t for just a minute to give a direct way to deal with t. In fact, this will be slightly repetition. That matrix t factored into, like all good matrices, factored into upper triangle. You know, we did elimination, and we ended up with some upper triangular u, and the lower, it turned out to be u transpose u. It turned out to be, yeah, best to look at that again. U transpose u, u was 1s on the diagonal. The pivots all turned out to be 1s and minus 1s just above. And then its transpose has 1s on the diagonal and minus 1s just below. And if I multiply those matrices, I get t. All right. So then the idea was, okay, maybe we can invert those pieces. And we can. So let's now so that was t. Then t inverse was the inverse of u times the inverse of u transpose. And so if I want to invert this guy and put it here, oh, am I going to get, okay. What's, yes. What's the inverse of this one? Let me fill out. There's u. So I want to put, its inverse comes first. So we've done this before, but do you remember what the inverse looked like? I have here a upper triangular matrix. So what can you tell me about its inverse? Also upper triangular. And this is a difference matrix, and its inverse will just be a sum matrix. So this is what turned out to be the inverse of that. And then the inverse of that was the transpose, so it's now sums, now good. Okay. So that's all quite quick to check. I mean, I'm doing it even more quickly here, but it would be quick to check. And that gives us our answer, right? When I now if I do the multiplication to find t inverse, I'm just going to multiply those guys. Okay, I get from that I get the 4. And that times the next one gives me 3 1s, produces the 3, then the 2, then the 1. That row times that column will be the 3 here. I'll get this formula. No problem. Okay. So that's all right. So I guess I feel that with t, we could legitimately say, yeah, we not only discovered the inverse, we found a system to produce it. Now, if I change over to k, it was not so easy. This method gives me triangular factors, but their inverses would take a little patience. But they're quite attractive still. But then multiplying the two factors together takes even more patience. So I would like to think of another way to deal with K inverse. So this is really my principal job, how to deal with K inverse. So one way would be the triangular factors, invert them, multiply, but somehow we wouldn't really see what was happening there. Okay, so now I come to K. All right, now I have two approaches to K. So T was easy. Okay. So one approach. Okay, let me tell you the one approach that I'll describe a little bit, but then it will be an important step in the Kalman filter in updating least squares. So it sort of links to the last topic on my outline. This occurred to me on the airplane, actually. What's the difference? Well, first of all, let me just figure out what the difference. I want to compare the inverses of T and K. If I compare, first, before the inverses, if I compare those matrices, what would you tell me about K minus T? How much have I changed one matrix to get to the other one? Just one entry. So what would you tell me about that matrix K minus T? It's all zeros, so it's incredibly small. I mean, incredibly simple, except for that single one, right, up in the corner. So what's the rank of that matrix? I'm interested in the rank. It's just one. Yeah, the matrix is just like this guy. The K minus T. Yeah, let me put out what K minus T is, because that's so simple. K minus T is this obviously is just this matrix with a 1 and all the rest zeros. And if that's a rank 1 matrix, that should be writable. I should be able to write that matrix, which is rank is surely 1, as a single column times a single row. And you can see what column times what row would produce that matrix. Well, just what shall I do for the column and what shall I do for the row? It's just 1 in the first place, yeah. 1, 0, 0, 0. That's a good, and 1, 0, 0, 0. And just the only interest in that example is just to remember that I can multiply this 4 by 1 matrix column times this 1 by 4 matrix and get a 4 by 4 absolutely following the rules matrix. And it's a rank 1 matrix because it's just a row times a column. Anyway, it's a very special rank 1 matrix because it's such a very special row and column there. Okay, now the inverses. The inverses. So let me take T inverse minus K inverse. And so what I want to say is that if two matrices differ by a rank 1 matrix, their inverses differ by something special. And I propose that we just figure out from this, try to see the pattern by just doing the numbers for this example. So this is one approach to finding K inverse. So this approach to finding K inverse is to sort of compare with T and compare the inverse with T inverse because T inverse is simple. So that's one way to do it. Another way will be more directly just go for K inverse and to heck with T. Right. Okay. But can we subtract T inverse from K? Subtract this from this? It took me a couple of tries, but we can do it here. So what's the difference between those? T inverse minus K inverse. Can you do that? So I have 4 minus 4/5. Well, obviously I'm going to need a 1/5 factor, right? So I'm just doing this calculation to see something interesting. Because I think it's more fun to discover stuff than just announce it. Okay. So I have 4 minus 4/5 is how many fifths? Just tell me the number of fifths. 16 fifths, right. 20 of them minus 4 of them. Okay, what goes next here? I have 3. That's 15 fifths, and take away 3. What number? How many fifths have I got here? Help, help. 12? Yeah, 12 sounds good. I'm just subtracting. This is the big one, and that's the small one. Okay, then I have 2, which is 10 fifths. Take away 2 of them. How many fifths? 8. And finally, I have 5 fifths. Take away 1/5. Leaves me 4 fifths. Okay, good. Now, let's see. Everything's symmetric, right? Will you let me fill in this much without stopping? Okay, now how about in the middle here? I have 15 fifths minus 6 fifths is 9. And 10 fifths minus 4 fifths is a 6. And 5 fifths minus 2 fifths is a 3. And again, symmetric, so I can be pretty sure that it's 6 and 3. Would you want to predict the others? And then 4, 2, right? Let's put them in. 4, 2. And do you want to predict the last one? 2, 1. Okay, and what, should we just check one of those and regard it as safe? Okay, is the 1/5 correct? Yeah, because I have 5 fifths, take away 4 fifths, does correctly give 1/5. Anyway, that's right. And what's special about that matrix? Tell me something special about that guy. It's rank 1. Yes, its rank is 1 again, because every row, all the rows are multiple. I mean, if that's the bottom row, that row is twice as much. That row is 3 times as much. Actually, it's rank 1 and with very special numbers. What would be so I could make it 1/5 of, well, tell me the number there, the row and the column and the row that would, 4, 3, 2, 1 would do it. And because it's symmetric, my 2 vectors can be the same. Rank 1 matrices in general have this form, column times row, and if they're symmetric, the 2 vectors are the same. Okay, so, well, that's very pleasant, and then I thought, there must be a formula that would tell me that, and it must be quite important. So the formula is, what's the, if I know 1 inverse, so I know this, and I know all of these guys, and I want to find that. And so the formula for what is K inverse if you know T inverse. Yeah, and shall I write that formula down, but then I won't pursue it right now, if that's all right. It's the key formula for all updating problems and estimation. I guess I feel it's a key formula for the kind of scientific problems that mathematical questions that would come up here at the lab. Because we're doing estimation. Yeah, can I just continue my conversational part without the formulas? I guess it seems to me that a key problem is we're doing least squares. We're doing estimation. Where is that satellite or that missile? And then we get another measurement. So that's one more bit of information which updates, gives us a correction to the estimated position. And because that is just one more bit of information, it's like somehow it's a rank 1 change in our estimation problem, and then we're looking for the change in the answer. And that's what recursive least squares or the Kalman filter and filtering is all about, is updating from new information, updating the old answer with new information. Okay, and that's what we're doing here. I guess I'm regarding, here is T inverse is our old answer that we found because it was especially easy. And now I'm updating by that much, and I'm looking for the new answer. Okay, I'm just going to write down the formula then that we will see later. So the new answer that I want is the old answer. And then in comes, this K minus T is this rank 1 matrix. Yeah, maybe should I just keep it as K minus T? I think maybe here's the magic formula. If I can do it without my eyes, I think it's got to involve only T inverses. And K minus T and another T inverse. That looks pretty good. And now down below, I think is something like 1 plus, ooh, geez. Oh, I got to get a number here. That was good. Down here, oh, so I have to say what these two, this rank 1 matrix splits into, what name shall I give to that vector? Can I call it little e or something? Little e is that column vector, and then this is the row vector. Okay. Okay. And so what shows up down here, I think, is T inverse. Oh, maybe it's, no, it's the E is the other side, because I have to end up with a number. It's E transpose T inverse E, I think. I think that's right. I might not have all the signs right. But do you see the beauty of that formula? If it's right, of course. It's almost right. If it's not. And about 100 people have discovered this formula. And they all thought wonderful, and they all got their names attached to it. So the formula has so many names now. I could mention, somebody named Woodbury, who, then an old-timer named Schur. When I do this formula properly, I'll produce more of the names. But do you see that it has exactly what we hope? Because what do we know here? We know T and T inverse. So there's T inverses, and we know K. And this is a rank 1 matrix, and this is just a number down here. So we know everything here, and it gives us the inverse of the new one. And if I did it right, it would produce this correction. This whole stuff would be this correction term, and we would have our answer. Okay, now I don't know if that's entirely satisfying, because that formula got produced out of thin air. And quite thin air. And what I want to say is just really looking ahead, that this formula, if the change in the matrix is some rank 1 matrix, then the change in the inverse is also rank 1. It's a more complicated looking thing, but this guy is the rank 1. So the whole thing is rank 1. And there it was in this particular instance. Okay, so I was quite happy with that. I thought, okay, that connects to later parts of the course in a beautiful way, shows our formula, shows this formula from later on to be, which will come in March, to be actually very useful for this puzzle that we never really resolved. But now I'm going to turn to a direct attack on this inverse, because we can get it directly too. And getting it directly will connect to our differential equation. So I'm proposing to erase this. If nobody objects, I'll erase this rank 1 and this wonderful formula, because we'll see it again. I'll just mention, though, I hate to erase it totally. Let me tell you one application of it. One because I spoke about these squares there. Yeah. So let me complete that thought before I give up. Suppose I'm trying to find the position of this darn thing. And what I'm given, so suppose I'm trying to solve these squares problem. AU equals some measurements B. Okay, now what's my A? My A is going to be, it's going to be rectangular, and it's going to be a matrix with 1s, minus 1, 1, minus 1, 1, minus 1, 1. So it has, so far I've got, and a final guy, minus 1. All right. And I'm looking for the positions of this, let me say, satellite, and I measure B1, B2, B3, B4, and B5. Okay. What's up here? It shouldn't have. Does it? 4. I hope 4. 1, 2, 3, 4. Yeah, it's good. Thanks. Oh, that's critical. So let me just say the problem in words. I'm trying to this satellite is in it's moving along. So I first measure its first position. So I make a measurement. U1 equal B1 is my first equation. Plus error. Okay, so I know approximately where it is. Now the second equation is U2 minus U1 is some B2 plus error. So what have I measured there? I've measured the difference, how much it moved, right? So I didn't know exactly where it was, but the second measurement told me something about where it is now by measuring the relative error, which, of course, everybody can think of applications where that would be the case. And then the third equation would be a measurement of the next one, and plus error, and the next. And now I pretty well know, I know something about U4, because it's approximate. Well, so what is U4 is approximately what? I guess if I just had those 4 measurements, what would be my best guess for U4? I'd add those, right? If I wanted to know U4 out of these 4 measurements, if I add those equations, that would give me U4 equal B1 plus B2 plus B3 plus B4 plus errors. And that's like the best I could do. That would be the best least squares. Now, right now I've only used 4. Okay, and that's exactly, so that exactly corresponds to this matrix T. If, oh yeah, so what, do you remember what to do with least squares? What's the equation? So if I have a rectangular system, as I do here, there's not going to be a solution. So I'm looking for AU approximately as close to B as I can get it. And what equation do I solve? That A transpose A, right. So that leads me to the A transpose A equation. That for the best U is A transpose B. That's the equation I actually solve. Now, when it was 4 by 4, then I had 4 equations, 4 unknowns. Actually, the matrix was completely invertible. I could solve it directly, and you gave me the best answer. U4 is the sum of the B's. But now I get a 5th measurement. And that 5th measurement is minus U4 equals someplace B5. Well, basically, it's a measurement of plus error. It's a measurement of where that final guy is, but it's got error in it. Now, what's the best estimate for U4? Let me ask you that. What's the best measurement for the final position, the best estimate of the final position U4 based on 5 data? 5 data. You might say, okay, the last measurement was measuring U4 exactly. Couldn't do better than that, but you can. Because you had information previously, and you're not going to throw that away, right? There's error in this measurement, so it's not exact. And there's error in these measurements, possibly greater error because it was like compounded, but still information is in there. So the least squares method uses all the information you've got by computing A transpose A. So, yeah, so what's the connection with K and T, our particular matrices? It's exactly, that's what A transpose A is. The 4 by 4, the 4 measurement case, A transpose A was the T. And the 5 by 4 problem, the 5 by 4 case with this last guy, A transpose A, which now has a new thing. Oh, it might have been the T, or it might have been, yeah, it might have been the H. It might have been the upside down T. Yep, probably was. But the 5 by 4 one is the K. Right. So, so that's the practical problem. That's to me that seemed like a beautiful model problem. To have information on the starting position, on the relative change, on the differences, and then yes, later to get a new information about the final position, and then to update to get to a different U hat, which uses this from the old U hat, which didn't know it. That's exactly this move from A transpose A being the T or the H to A transpose A being the K. If I took this matrix and multiplied by, yeah, I guess if I took that as it stands and multiplied by its transpose, I'd get K. I'd get 4, right? The 4 by 4 example that we've done. Okay, so my point is that this is not just matrix manipulation for the heck of it, this lecture, but that it connects directly to a typical model problem in least squares and the key issue of updating the estimate when we update the data. And that update produces the change from T, or maybe it was actually the upside down matrix H, to K. All right, so that's, I hope that's like it's now permanently on the web, so we can return to that when that lecture comes up. Okay, now so the rest of this lecture is the direct attack on K inverse. And at the same time, we'll get T inverse. Okay, so I'm going to make space for this direct attack. Okay. Well, that much space for now, and then more space later. Okay. Okay. So I'm given the matrix K, the fixed matrix, and I'm looking for its inverse. Everybody recognizes I still have not written down the formula here. So somebody suggested to me by email, but I haven't written it down. Okay, so I'm still looking for it. I could create it out of this update formula, but I'm going to go directly. Okay, so how do I find? All right, let me prepare the way here. I want to prepare the way. Do you remember in the differential equation case, we prepared the way by introducing the delta function, the step function, and the ramp function? So those were delta, S, and R. The jump was at 0. The action happened at 0. Okay, I just want to do the same for vectors. I want to have a delta vector, a step vector, and a ramp vector. And it's just going to be exactly what you think. So let me graph the components. Say the vector will go forever. So the components of the delta vector will be those. The delta vector is going to be, delta I is going to be either 1 or 0. 1 at there, right? Okay. Then the step vector is going to be 0, 0, and then at this position it jumps. So that's the step vector. Actually, we could, now everybody remembers these guys in the continuous case. Now we're doing the discrete case. So what's the step vector? I should have maybe filled in here. The delta vector, I mean, that's the standard notation, actually. It's 1 for I equals, tell me the delta vector here. If I is 0, delta 0 is 1. And all other positions, it's 0. Fine. Okay, what's the step vector? The step vector, Si, is, well, 0 for I negative, and 1 for I, 1 after that. And finally, the ramp vector. So this is, somehow I had never thought about this ramp vector, but of course I should have. So it has a 0, a 0, a 0 at position 0. Then it ramps up to 1 and to 2. So now here's the ramp vector, Ri. And what's the formula for Ri? Always these two-part formulas, to the left and to the right of the center point. Okay, so the ramp vector is 0 to the left. And what is it on the right-hand side? I. That was exactly right. Very quick. Yeah. So it's going up. So it's up 1, 2, 3. It's I for I greater or equal to 0. And notice it matches. It agrees that I equals 0. I agree. So I get the answer 0. Okay. So that's like preparing the way by just seeing these very satisfying delta vector, step vector, and ramp vector. Okay, now for my direct attack on, so what equation am I going to solve? I want to solve I want to deal with this matrix K, U equals, now what shall I take for the right-hand side? Well, my message is, let the right-hand side be a delta function. That was the message in the differential equation, where I got beautiful, simple, two-part answers. And it's the same message for the matrix equation. Take the delta function. Say delta, but I'm going to, the point was the delta function got moved wherever I wanted, so the delta vector will get moved wherever I want. So I'll move the delta, so this will be the delta vector moved over to spike at J. So I have, in other words, I'm going to solve it for several right-hand sides. The J equal 1 case, I'll solve for this right-hand side. J equal to 2 case, I'll solve for this right-hand side. J equals 3, I'll solve, the right-hand side will be that. And J equal 4 will be that. I'm taking, those are there are only 4 possibilities here. Where here, A could be any number between 0 and 1. I could move it wherever, I mean, it was continuous. Now, why am I interested in those right-hand sides? That's the question. What's interesting about those right-hand sides with KU equal F? They're the columns of the identity, yes. They're the columns of the identity. And so over here comes my K, and now I have my 4 answers. So let's put in my 4, well, I have to find those 4 answers. But the reason I'm interested in those 4 answers is, so here's answer 1. This is the answer for that right-hand side. So whatever it is, this is the answer for that right-hand side. This is the answer for that one. This is the answer for that one. And now again, why am I interested in doing this? Because that will give me the inverse. Right, so it'll be sitting right there. Because multiplication of matrices is by columns, can be by columns. A good way to do it is by columns. K times the first column of the inverse gives the first column of the identity. K times the third column of the inverse gives the third column of the identity. So if I can find those, and actually, we see what they better be. That first column had better turn out to be 1/5 of 4, 3, 2, 1. But let's figure out why that's correct. And that second column had better turn out to be 1/5 of 3, 6, 4, 2. Why is that right? And more than that, what would it be for n by n? So eventually I want to get to kn inverse. That's my goal, of course. For specific 4, I can figure out the inverse or somehow get it. Okay. So do you see why I'm interested in those problems, in those 4 particular right-hand sides? Okay, and now I ask, okay, what are the solutions? Well, now, where does this ramp come? So remember, what's the k doing? The k is this, remember what my k matrix is? It's up there. It's got this -1, 2, -1 stuff, with a -1 kind of lost out there, and -1, 2, -1, and -1, 2, with a -1 kind of lost out there. The K matrix is a second difference matrix, which you told me before. Now, what's the answer? What was the answer like? What was the answer in the? What was the answer you like in the differential equation? You remember? What was the second derivative? Was a delta, and what function had second derivative equal delta? Ramp. It was r. So what do you think will be work in the matrix equation? The discrete r. The second difference, so this is the great point then. The second difference, how shall I write that? Delta squared maybe for second difference instead of second derivative, and maybe, yeah, equals the second difference of what? Well, the second difference of the ramp equals the delta vector. That's really what I want to do. This is the key point, that if I took this vector, the ramp vector, and took its second differences, what would I get? All right, can we just patiently do that? What's the second difference at that point, around that point? So I'm taking one of those minus 2 of that plus 1 of that, but of course it's just 0. What's the second difference at this center point? It's 1 of those minus 2 of those, 1 of those, which is 1, right, because it's 1 of those. And that's the one there. No, that's the one there. Right. And what's the second difference around that point? It's 1 of these minus 2 of these and 1 of these, which is 0 again. Right. And around this point, 3 minus 2 2's plus a 1, 0. So I get all these zeros. Yeah. So, I mean, you could say, oh, well, big deal, because it was exactly like the differential equation. But in a way, it's easier to have like just one idea and see it appear in the matrix case. So the solution is going to be a ramp. Well, what was the solution up here? I have to remember it again a little more. It was a ramp plus what? Plus a constant. Yeah. So the solution up there, the u of x solution, was the ramp function. Well, actually negative the ramp, because it negative the ramp, shifted over to a. That solved the equation. And then there was the other bit, what else was in that solution? Remember that, here's a second order differential equation. We've got a particular solution. We move the ramp over to A, and we reverse sign to take care of that. What else? What's the rest of the solution here? AX plus B. Right, AX plus B. Because second derivative, this is the homogeneous solution, the null space. The second derivative of that is 0. So that's got the two integration constants in it. Okay, ready for this guy now. What's the solution UI for this guy? I want the second difference of U to give me this delta, which is now centered at position J, J being different in these different cases. So I'm just going to copy this for the, I'm going to say it's minus, because I've got this, K has got this minus in it. And it's this R. It's this ramp vector, again, shifted over to center at J where the right-hand side, where the right side is centered. And now what else are you going to allow me to add on? I could add on, so what am I allowed to add on? So now this solves the equation, but I need a couple of constants to play with because I've got two boundary conditions that I have to match. So what's the analog of AX plus B in the discrete case? So X was our running variable. It's just I. I think if we just we could just have AI, any multiple of I, that'll be any constant. I believe that that's the solution, the general solution to the equation. Because this solves with the right-hand side, and then this is the usual stuff we throw in. Constants of summation, I guess, would be the right word. Because when we have differences, we invert by summing. Okay. Do you see that that's reasonable? In fact, it's okay. So that now for each J, we have to find these constants. So what are our boundary conditions? Our boundary conditions, I guess, were those. This was our fixed problem with boundary condition 0 for U0 and 0 for U5. Those are the two guys that were lost at the ends of the interval. Those are the two displacements that were fixed if we were doing that line of springs. So I need to, for each J, I need to plug that in for J equal 1, then for J equal 2, 3, and 4, and plug in I equals 0. Oh yeah, we could do that. Come on, let's do it. Let me plug in I equals 0 and I equal 5, n plus 1. So what happens if I plug in I equals 0? This is quite pleasant. At I equals 0, just the way we plugged x equals 0 into the differential equation, now I plug I equals 0 into the discrete vector case. So, and I'm supposed to get the answer 0. So what do I get? What do I get from that? 0. What do I get from this? That's the ramp at 0 minus j. That's the ramp off to the left. It's 0. So what do I learn? B is 0. Got one of those constants nailed, and fortunately it's 0. Okay, so B is now gone. I've used that boundary condition, U0 equals 0. And now I'm ready to use UN plus 1 equals 0. This is, now can I jump to the n by n problem? So now at n plus 1. So what's happening here at n plus 1? Now plug in. Now I'm going to learn A, probably. So I'm plugging in. Where am I plugging in? N plus 1? Yes? For I, and I want the answer 0. So I want 0 to be, now what's minus, what's the ramp function when I plug in n plus 1? Well, it's n plus 1 minus j, right? That's what it was climbing. That's what the ramp did. It just climbed right up. Okay, so it's minus n plus 1 minus j, and now plus a times n plus 1, which was the I. So because I'm plugging in I equal n plus 1, and I'm trying to get the answer 0. So I finally learned what a is. I learned what a is here. And now I'm ready to write down the, now I've got this is column J of the inverse matrix. I'm ready to write down the inverse. So trumpets to sound at this point. Okay, so this direct approach by perfect analogy with the differential equation gave me the formula. So let me write it down again. This is the inverse. This ui with the source term at j is the inverse ij. This is ui. This is ui with source at j. Okay, now can I just write it down? So it's minus this ramp. Ooh, what is that ramp thing? Plus a, I know. Shall I put a in first? A is, do you see what a is? A is n plus 1 minus j over n plus 1. That's the a times I, minus the ramp. We're going to have it here. So that was ai. And now minus this ramp. So what does the ramp equal? Well, it's got two parts. So now this was ai. And this is going to be minus. This is going to be the ramp at n plus 1 minus j. Is that correct? Yes. So what is it? So if j, is that right? N plus 1 minus j? Yes. Oh, that n plus 1, sorry. That n plus 1 was when I was plugging in n plus 1. It was I minus j. It became n plus 1 when I was figuring out this constant, but generally it was I. So I just want ramp of I minus j. We're done, and thanks for patience here. Okay, so what's the ramp thing equal? Ramp I minus j, we get a 0 if I is less or equal to j, and we get a I minus j if I is greater or equal to j. Okay. That is the inverse matrix. Well, we could do, I think, to be on the safe side, we ought to check it. One entry, will you allow me just to check one entry of the inverse? And you can say which one. Okay, here is the matrix that is really the inverse. Which one would you like me to check? The 6, maybe? That's the most sort of, where did that come from? Okay, the 6. Okay, so that's I equal to 2, j equal to 2. Is that right? N is 4. Okay, so I'm checking the 2, 2 entry, and if that's right, everybody has to concede that they're all right. Okay, okay. And before I put in the numbers, can I just say the pattern that one should observe here? You observe that the numbers grow linearly, starting from 1 in that last row, and up the column, and then they grow linearly here. So on one side of the diagonal, 1, 2, 3, 4, including the diagonal, 2, 4, 6, 3, 6, 4, we see linear growth, right? That's the pattern you should see. And then symmetric on the other side of the diagonal. So it's that pattern which people could notice, guess the answer, and better be in our formula. In other words, it better be linear, which it is, but separately, this is above the diagonal when the row number is smaller than the column number, and this is below the diagonal, so two different linear functions, but both, and that's what we had up in the continuous case, two different linear functions that met at the diagonal. Here, okay, now I promised to end by checking, what did I say? We're doing n equal 4, we're doing I equal to 2, and we're doing j equal to 2. Ha! So, let's see. 4, that'll be 5 minus 2 over 5. 3/5 of 2. 3/5 times 2. Have I cheated yet? No. And what's this thing? It's 0, right? Because the one you asked me for was I equal 2, j equal 2. It's right on the diagonal where we get 0 from both parts. So the answer came out 6/5, and that was the correct number. Would you want to do one more? My nerves are feeling better now. I'm ready to do an off diagonal one. Say here. Let's do that one, where the answer should be 3/5. So that's the case where j is 4. We're in the column 4, and I is 3. So can I switch to I equal 3, j equal 4? Just, and n is still 4, just for fun. Okay. But the key is that the key point, of course, is in this second approach. The first approach was that rank 1 change. That was important. The key idea here is the perfect analogy between differential equations and difference equations, and between the solution to the differential equation and the solution to the difference equation. That's with delta functions on the right. Okay, finally, just this number. Let's see. So I have 5 minus 4 is 1 over 5 times I, which is 3. And then, well, what's this one? Oh, it's 0 again. Yeah, above the diagonal, 3 is smaller than 4. I'm above the diagonal 0, so 3/5, and that was right. Okay. So that completes probably more than you wanted to know about K inverse, but I really think it's the clearest model we could produce of second differences imitating second derivatives. And in real problems, in a way you could say, okay, the second differences part was messier. It wasn't quite as clean as that one there. And probably that's true in general, that finite differences are to analyze, to get exact formulas. The exact formulas are not as nice as the calculus formulas. Yeah, I mean, that's sort of a fact, that if I add up the numbers 1 plus 2 plus 3 plus 4 plus 5, I get something, and there is a nice formula for it. But, or adding up the squares, 1 squared, yeah, compare adding up the squares. 1 squared plus 2 squared plus 3 squared plus 4 squared plus 5 squared. Okay, Gauss has got it figured out what that was, right? But we don't need Gauss to do the continuous case. If you ask me to integral from 0 to 5 of x squared dx, that's child's play, right? So the calculus problem is easier if you want to do it yourself, so to speak. But if you want the computer to do it, if we switch to scientific computing, then the matrix problem is the easier one. So the computer deals fine because it doesn't figure out any formula like this. It just plows along and finds the inverse matrix by elimination steps. and ends up with something nice in this case, in other cases not so nice, but it gets the answer. Where if we give, so we could give the, going back to Laplace's equation for the lecture before, I can't give the computer Laplace's differential equation on some strange shape and expect it to give me an answer, but I can give it a finite difference equation or a finite element equation, and it will certainly give me the answer to that, which will be approximately the other answer. So it's those parallels between the applied math that we could do in detail with nice formulas sometimes, and the computing that we could do always. Well, MATLAB can do it. And occasionally we get a nice formula when the problem is as perfect analogy as this one with that. Okay, so that's completes lecture 10. Thanks very much for allowing me to